So we've been operating kind of at the interface of where biometry, remote sensing, and fire science really interact, and how we characterize the natural world for both making silvicultural and fire management decisions. And to do a lot of this, we're using technology called structure for motion, where we fly the forest taking photos at fixed overlaps between the photos. And having that overlap, just like your eyes give you depth perception, having multiple photos saying the same thing allows us to create a depth of image that allows us to create what's called a point cloud, or a vertical structure of the forest. And so we can actually map the height of the vegetation spatially across the area we're working with. We've been working the last several years to create different algorithms to extract the individual trees in the forest. And at this point, in some of these lower montane forest systems, more ponderosa pine or mixed conifer dominated systems, we're getting typically somewhere around 90%, 95% of the trees within a stand that we can actually map the location, height, the crown area and crown diameter, the crown base height. We have modeling techniques that allows us to estimate the crown biomass within the individual tree. The Forest Service has done a great job adopting some of these technologies for different applications, particularly in the fire world, and they're really just starting to take hold in the more of the natural resources and forest management world. And so some of the things we're interested in trying to see if we can improve efficiencies on and help improve safety with is to map things like beetle kill, where we have a higher potential for tree blowdown while we have crews in the woods. So if we can have a drone map these things and we're standing on a roadway to do it, we can hopefully eliminate the hazard of sending a crew into a forest with dead standing trees. The other big area we're trying to move this into is finer scale understanding of how fire is going to interact both with the terrain and with the three-dimensional structure of the vegetation itself, so that we can hopefully optimize how we do things like prescribed fire ignition patterns and the timing and prescription windows for the fire behavior that we want to have. As this technology advances, the hope is that we can reduce the burden on field crews and how much time they have to spend collecting field data, and that's one of the most expensive things the Forest Service does in the field. With the drone, we've done as many as 400 or 500 acres in a single day with the drone, and we're getting to the point that we can have that data ready to use out of the drone in 12 to 24 hours, which really makes enough data available that we can significantly reduce the cost of that field data collection. I've been working with colleagues at Colorado State University who've come up with algorithms in a laboratory that really allow us to use the imagery the drone is collecting to assess the moisture content of the foliage of the individual tree. And so now we're working on how well can we scale that across the landscape, so that when we go in to make management decisions, we can look at, are there places in a stand of trees that are already more drought stressed, and make decisions on should those be the places we should be implementing treatment, or that may have persistently had openings historically. We're trying to model individual tree fire effects. So we're looking at the crown scorch, or the volume of the crown that gets scorched in the individual tree. And we're doing that on prescribed fire operations to try and provide feedback to the managers, the decisions they make about how they put fire on the landscape and how that translates then to the trees they're impacting. And so we can relate some of the tree characteristics like the size of the tree with the fire effects they're having at the individual tree scale to hopefully provide managers feedback on how they're doing their prescriptions so that they can adapt and overcome any challenges they might interact with. If we can map trees like these, we can also do spatial restoration within these systems, because we get a spatial map of the individual trees. So we can really start moving into what's considered precision forestry and getting the exact outcomes we want, because we know the trees we're looking at ahead of time.